Okay. So my entire screen. I don't know what this is. I have to use my husband's computer because mine doesn't have a webcam, and every single time all these little ads pop up on the side. And I have to. It doesn't happen until I try to start presenting or talking. Okay, can y'all see this PowerPoint?
Yes.
So first I wanted to go over the 10% condition because there was some good questions on it and I wanted to clarify. And then after we do that, we'll go over the Super Sixes. And then I want to talk about just a few more materials I posted on Google Classroom for y'all to use for your last week so that y'all have 1 week to your test, which is crazy. So you should be feeling pretty like just wrapping up little things. But for the most part, you should be like, if you take your test today, you could do it. So 10% rule. We know that it's a condition you meet whenever you're doing like a confidence interval or significance test. And what is it? Is we know that it means the sample size should be no more than 10%, or the way I think about it is in parentheses, the population needs to be 10 times the sample size. Right. So if your sample size is 50, the population needs to be about 500. And so then I think y'all are good with that, but why do we need it? And when do we use it is the more important question. So why do we need the 10% condition? To prove each person or trial in a sample is independent of the other because you're sampling without replacement. So an example is like if we are sampling people that come out of a mall, theoretically, when a person leaves, now our population has changed because we're not putting that person back once we sample them. But if our sample is 10 people and the mall has 10,000 people in it, one person leaving isn't really changing your population. That's why you want your sample. You want your sample to be less than 10% of the whole population. So that way, when you're taking one person out at a time, it's not really changing the population. You can still use your sample as a representative group of the population. So it's proving, so if it asks why you need it, that would be the answer, to prove that each trial in the sample is independent when sampling without replacement. And so when do we use it is anytime we take a random sample without replacement. So if you're doing an experiment and you only have random assignment, you don't need the 10% rule. But because of that, the reason we're talking about this is because we were in the last AP video for one of your mock tests. He checked the 10% rule and he did it with a different number than because when we do like a 2-sample t-test, normally you have 2 different populations and you do all your conditions separate with 2 different populations. But when he did the 10%, you just do it for whatever random sample. So even though it wasn't an experiment, if you looked at the first line, it said that they took a random sample of 50 people and then used that for the experiment. So use your 10% rule for whatever random sample was taken. And then your 2 treatment groups was like your 2 different populations. So it was like a 2 population deal when you do all your work. But for 10% rule wise, you just care about whatever random sample was taken. So if they took 2 random samples for 2 different groups, then you would have to check it twice for each random sample. But since they only took 1 random sample, they checked the 10% rule for that random sample, and then they gave 2 treatments. So each treatment is like its own group and population from there. So for the rest of your work, you treat it as like 2 separate populations, but it came from 1 sample. Does that make sense? It's very quiet. I can't see your faces, but I don't know if that's a good thing or a bad thing. We good on 10%? Now I can see y'all. Okay. Also, I put a YouTube. I can post this PowerPoint when we're done. But I put a YouTube link to, I think it's Khan Academy, where he really breaks it down on why we need it and the idea behind it. So if you really want to understand it more, you can watch that YouTube video. Okay. So now let's go over the Super Sixes, and we can try to do this pretty efficiently since we don't have that many people. Just make sure everyone has the answers and the idea. And I posted a few things on my PowerPoint of ideas that I want to make sure I cover because you might have not done it the same way. But there's 2 of them, so we're going to start with the 5th one. It says number 3. And I think pretty sure we've done one like this before. So it says train. I'm not going to read this, but the idea behind it is that if it's functioning properly, the actual weights of ore loaded into each car by filling equipment at the mine are approximately normal with a mean of 70 and standard deviation of 0.9. If the mean is greater than 70, the loading mechanism is overfilling. So just keep in mind, if one car for me, I don't know why, but this word problem, it's hard for me to like say the right words in context because there's so many different things going on. But yeah, if one car is overfilled, that doesn't mean it's overfilling, right? You're going to have some that are greater than 70, but if the mean is greater than 70, then it's overfilling. So just keep that in mind. It's okay to have one car that's greater than 70, but we don't want the mean to be greater than 70 when you average it all together. So part A said if it's functioning properly, which that just means if the mean is 70 and the standard deviation is 0.9, what's the probability that the weight of the ore in a randomly selected car will be 70.7 tons or more? So what'd y'all do for that one?
I just did normal CDF in the calculator with the lower bound 70.7, upper bound infinity, mean 70, and standard deviation 0.9.
Awesome. And what'd you get as your answer?
I got 0.218.
I did too.
Awesome. And then go ahead. So make sure when you do that, you label all your stuff that you type in the calculator. You need to mean equals, standard deviation equals, lower bound equals, upper bound, especially because since it's online, I don't think they're requiring any diagrams. Like you don't have to technically draw that distribution. Now, if you're doing it on paper, I would go ahead and draw it to be safe. But if you're not drawing it, then you especially need to make sure you label all your numbers. I wouldn't even do LB, UB. I would write it out to make sure. And then I would also put it in a sentence. When I was watching those AP videos they were posting, I feel like they were very adamant that you need to write it out in a sentence at the end. So just rewrite the probability that a weight of the ore is randomly blah, blah, blah is, you can either change it to a percentage or keep it a decimal. So this is the only one I'm going to add some extra stuff and then I'll let y'all just go through and check. But I want to talk about z-scores just in case they find a way to ask. Because if you do normal CDF, you don't have to standardize it. But let's say for some reason they asked you to use your table, or I don't know how they could do it, but I feel like they could find a way to ask this and make sure you have to do it this way without doing normal CDF. So if you didn't have normal CDF, you would have to first standardize it by converting your value to a z-score. So our z-score formula, if you don't have this written down somewhere on whatever you're going to use the day of your test, I would write it down, but it's z equals your observation minus the mean divided by the standard deviation. And that's your z-score, 0.778. So it's like, instead of the mean, the middle of your distribution being 70 and the standard deviation being 0.9, now the mean is 0 and the standard deviation is 1. But it's like if you converted all your data, 70.7 would fall at the same spot as 0.778. So that is what I put here in red. And so then this table gives you the area less than. So you go find your z-score, you go to the left column first, and since it's 0 in front, I put 0.7, and then I went over here to the hundredths place is also a 7, but then it was 8, so I really could have probably like found the middle value between this 0.07 and 0.08, but I don't think it's that crucial. But I went with this one. So this number right here for that z-score is 0.7794. So that would be the area less than the z-score, but our problem asked for being greater than. So then I did 1 minus that area and got 0.2206. Okay, so I kind of showed this notation as well, So we were looking for the probability of our observation X being greater than or equal to 70.7, which is equivalent to the probability of, once you standardize it, now it's Z instead of X being greater than or equal to 0.778, the Z score that went with that observation. And then I got that area. So that is how you would do it using Z scores. But it should be, now your number is going to probably be off because I rounded mine. If you do normal CDF, that's actually more accurate. So it's okay if yours was a little different once you do CDF. We good there?
So will they maybe ask us to use a table instead of a calculator for something?
I've never seen that. I just, want to be prepared because I feel like they keep saying it's calculator neutral. So I don't know how they could do it, but they could. So I just want to make sure y'all are prepared for anything. So I would print out, I posted on Google Classroom, I think like yesterday, the formula chart and all these tables. So I would make sure you have those handies just in case. Now, could you use normal CDF to check your answer? Sure, but I guess they could ask like to show your work standardizing it and getting the Z score. So I don't know. Again, they've never done that on like a normal AP test. I'm just thinking on different things they might do this year. Okay, so that's the only thing I'm going to add. You technically could use these scores for a lot of these questions, but we're just going to go through. And if you have more questions about converting to Z scores and using the table, just let me know. But we'll just go on and check it from here. So part B said, suppose that the weight of a randomly selected car is 70.7. Would that fact make you suspect that the loading mechanism is overfilling? Justify your answer. So what'd y'all say for that one?
I said no, because a significant amount of cars, nearly 22%, are being filled at or above 70.7 tons.
Perfect. Everyone agree? There was a pretty high probability, 20% chance that it was going to be that or more. So that's not small enough to where we're like, that seems a little off. So that concept is like kind of building to the idea of a p-value, right? A really small p-value makes you reject whatever we hypothesized is true. But if it's a large percentage, then we're not suspect. We're like, okay, that could happen. It's not that crazy or that weird that we got a car that's 70.7 if the true mean is 70. Okay, part C. What is the probability that now a random sample of 10 cars will have a mean or weight of 70.7 tons or more? What y'all do for this one?
I guessed on the number because I forgot how to do it, but I guessed a really small one because I figured that a random sample of 10 cars being much higher than that would be pretty small, if that makes sense. So
That concept makes sense. Anyone know how to get the numbers to support that idea? What's happening here? What are they doing now?
I did the plan and do of a significance test, but I got a really strange p-value, so I think I did it wrong.
No, I can't remember what the p-value was, but so I'm trying to think if you did the do of a significance test. Because really a significance test is to make a statement about a population value. We're just saying what's the probability of getting a sample mean of 70.7. So I'm not sure if what you did maybe got you the same answer, but what we're doing here is talking about, okay, so first we just said what's the probability of selecting one car that's 70.7 or more. Now we're saying, okay, what's the probability of getting a sample mean of 70.7? So this is going into sampling distribution. So to find this probability, theoretically, what we would need to do is take a random sample of 10 cars, record their mean, put them back, take another random sample of 10 cars, record their mean, put it back, take another random sample of 10 cars, record their mean, and then you graph them all and then see, okay, what's the probability of all these means being 70.7 or more? So what did I just describe? If I take a bunch of samples and record the mean for all those samples, we have a word for that. While y'all think about it, I'm going to pull up your formula chart. That's a sampling distribution, right? When I record a sample value for a certain sample size, like for a lot of samples, I want to know what's the probability. If I want to know what's the probability of getting a certain sample result, that's a sampling distribution. So how do I know the mean and standard deviation of a sampling distribution? You use your formula chart. So this is for proportion, but we're not getting a proportion from our sample. We're getting a mean from our sample. And it's just one sample. So you use this one right here, this first one. So the mean of X bar, which means the mean of our sampling distribution, if we take a lot of samples and record the mean for each sample, the center, the mean, will be whatever the true mean is. But the standard deviation of your sampling distribution will be the true standard deviation divided by the square root of n. So you get those two values, and then you do your normal CDF with those two values instead. Does that make sense, that concept now? So to show your work, you would say, okay, the mean of X bar equals 70 still, but the standard deviation of X bar would be the true standard deviation 0.9 divided by the square root of 10. Did anyone do that and get this?
Yeah, I did that, and I got the new standard deviation to be 0.285, and then I plugged that into the calculator using normal CDF. I said 70.7 is the lower bound, and then infinity as the upper bound, 70 as the mean, and then 0.285 as the standard deviation, and got 0.007.
That sounds right to me. Let's see. 0.0, yeah, if you rounded it. That's perfect. Does that make sense? So y'all just keep in mind this idea of sampling distribution. That's an important concept that I feel like is going to be on the test. But the thought process Molly had at the beginning is good to think about. Okay, well, the likelihood of a mean being that much greater than the true mean is a lot less likely than just one car being 70.7. Right. So as we go from the population to a sampling distribution, and then for that sampling distribution, as you increase the sample size, because every sample size has its own sampling distribution. That was a specific sampling distribution for a sample size of 10. If we changed our sample size to 20 cars, then we would have to go create a whole new sampling distribution, and the variance, the variability would be getting smaller and smaller, right, as we increase our sample size. So the likelihood of getting something out in those tails is going to get smaller and smaller. So I guess that kind of leads into part D. Based on your answer in part C, if a random sample of 10 cars has a mean or weight of 70.7, would you suspect that the loading mechanism is overfilling? Justify your answer. So now that we know the probability of that happening is 0.007, how would y'all answer that?
Yes, since there's less than a 1% chance of it happening.
Exactly. This is the exact concept of a p-value, right? We did all our work assuming it's correct, assuming the mean is 70. Well, if the true mean is 70, the likelihood of getting a sample mean of 70.7 or greater is 0.007, which is so small. You could say like how it's less than 1% that we think, okay, maybe the true mean isn't 70 because the likelihood of getting our sample result is so small. Okay, so E says draw a careful sketch, which you really should have already done in part A if you follow how we're supposed to do it. I can just show y'all this one. And like I said, on your AP test this year, they're not supposed to have sketches, but this is if you standardized it though, putting 0 and a standard deviation of 1, because remember my Z-score was 0.777. If you didn't standardize it, then you would put the center to be 70 and the standard deviation 0.9 and then shade it the same way. Part F. Didn't I say don't worry about? No, wait. Which one did I say don't worry about? Or was that the next one? That was this one. Never mind. Given the initial mean and standard deviation, how full are the most heavy 10% of cars? How would you do this one?
I used inverse normal. And so I used like the first sampling distribution with the mean of 70 and then did that the area is 0.1 and then the mean and the standard deviation.
And what did that get you?
I got 68.84.
Okay, so think about this. Because we want how full are the most heavy, right? And so the center of our distribution is 70. And you got 61.4, which would be less than that mean.
I got 68, yeah.
So do y'all remember what your calculator always does when you do inverse normal? What area does it always want?
The area of like if you're looking for 10%, it's the 90%, right?
Your calculator, whatever area you put in, that's the area they're assuming you want less than that value. Your calculator always does like percentile or area to the left or less than. So if we want 10% shaded to the right, greater than, you have to actually type in 0.9 instead of 0.1. It goes back to this table, just like how your Z-score table does probability or area to the left, so does your calculator. So just keep that in mind. But you had the right idea. So if you change the area to 0.9, you would get 71.152. Okay, describe the sampling distribution of the sample mean. So we already kind of did this one. You use the information in part C because your sample size is still 10. It's just writing it out. So how do you describe a sampling distribution? You give the center, shape, and spread. So our center, we already know, we said is 70. It's the same as the true mean. Our standard deviation, we did the true standard deviation divided by the square root of 10, and we got, what was it? 0.285. So the only thing left is to describe the shape. So how do we know the shape? I had to sneeze. It sounded like a cough, but it was a sneeze. How do we know the shape of our sampling distribution?
Can we use the, I don't remember if it's central limits but it's greater than 30, the sample size. So it's normal.
But is our sample size greater than 30?
Oh, I thought we were looking at H. Never mind.
Oh, yeah, for G, it's not greater than 30 yet. But that's okay because you only need to use CLT if it's not coming from an originally normal population. But because it says up here our population is approximately normal, you don't need central limit theorem. You can just say it's approximately normal because the population is. So that's what you would write down for the shape. So then part H says if we took a random sample of 40 cars instead of 10, how would that change your answer in part G? So what would change?
The spread, right?
Mm-hmm. The spread, right? Because that's the only one that's affected by your N, your sample size. And then you could either just talk about like hypothetically, if you increase your sample size, you decrease variability. So your standard deviation should get smaller, or you can actually calculate it and just show. Either one should suffice. Okay, we good there? Now this last one, talking about they wanted to test high cholesterol level by reducing either exercise or drug treatment, and then they developed a new drug, and they'd like to compare its effects on the currently available drug, and then volunteers who have a history of high cholesterol and who are currently not on medication will be recruited. So if you notice, this is volunteers. So there's no random sample. So if you were going to do some type of inference, like a hypothesis test or confidence interval, we would not need the 10% rule. So the first thing is it wants you to explain how you would do a completely randomized design. So I don't think I'm going to have y'all read it out, but what I want to show you is ideally, a good experiment has these 4 components. Now, the 2 that you really, I think, would have to make sure you write down is random assignment and comparison. I don't think, now, if you really want to make sure you just check all your boxes, I would talk about control, which normally refers to this second one, keeping all other variables the same. So anything else that could affect your result, keeping all those the same. And then replication, which means more than one person should be getting each treatment. But replications should be taken care of when you talk about random assignment. So you would just use some type of random assignment to give the current drug and the new drug. And then you'd be very specific on how you're going to randomly assign it. And then you talk about comparing the results. If you do those 2 things, you should get your credit when you're designing an experiment. So random assignment could be a lot of different things. Or you could do it a lot of different ways. You could put everyone's I think the safest way is assign everyone a number, put them all in a hat, draw the first half, and those get the first new drug, and then the ones left over get the current drug, or however you want to do it. Any questions on how to do a completely randomized design? Okay. If you need me to read yours specifically and let you know if you check all the boxes, I can do that. Just let me know when we're done. Part B says describe an experimental design that would improve the design by incorporating blocking. So what would be something that we would want to block by?
Maybe levels of exercise or initial cholesterol.
Those are both really good. You could do either of those. Because I mentioned exercise here, that's the one I would lean towards. But yeah, initial cholesterol would also be a thing. So as long as it's something, you pick a variable that you think would affect your results. And then I don't think you'd have to go too in deep, just to describe a design. So you would just say, okay, we would block or group by, let's say, exercise level, and then randomly assign each treatment within each block. Any questions on that? Just keep in mind you block based on something that's going to affect your results. You do not block on something random. So can the experimental design in B be carried out in a double-blind manner? So what'd y'all say here?
I said yes, but I don't really know if I have the right definition because I said that like single blind would be that the participants don't know what treatment they have, which you could do with like a placebo. But then would the second part of that be that the experimenters don't know who has which treatment? So yeah, so I said it could be double blind, right? As long as the person who like makes the hypothesis doesn't know like who.
Yeah, I think you're going in and out, but I got what you were saying. Wait, no, yes. So you could do it. Now, I think as long as you show your definition of double blind, I could see you giving two different answers to this, as long as you have the right idea behind double blind. So yes, you could if the subjects don't know which drug they're getting, and then who's ever recording the results doesn't know. Obviously, at the end of the day, someone's going to know who got what, or you couldn't compare. But who's ever actually interacting and recording what, like the difference, doesn't know, then you could do it double blind. Now, I could see the argument that because you're giving the new drug and the current drug, if those pills don't look the same, then you couldn't do it double blind. But if you had a way to make the pills look identical, then you could do it double blind. So I could see kind of either way. Just make sure when you answer a question that you show that you know what the word means. Give the definition of double blind in your answer, and you should be fine. Okay, so part D, we don't need to do describe. That's supposed to say part A right here instead of part C. And then if you did part A correctly, you should have already done that. So don't worry about that. Part E says, what inference procedure would you use to compare? I feel like, because they're trying to, cover all of AP Stats in 2 questions, they're going to use one of these where it's like an experiment and then you do inference from that experiment. So any ideas on what inference procedure, what name would we pick to compare the results?
I did 2 samples.
I said 2 sample mean.
Is that what you were saying, Becca, too?
Yeah.
I heard 2 samples, so I figured.
Yeah.
Yeah, good. It's 2 sample t-test because we got what you would do is you would have your current drug, you'd have your new drug, you would get the mean for each sample and then compare that to J-Mac. Sorry. You would have your 2 sample means and then you would use that to see, okay, is there a difference in the true mean if everyone, for the population of people that took the current drug and the new drug. So that would be a 2 sample t-test or mean test. In your calculator, it would be 2 sample t-test, but it would be mean. So what type of questions should you ask yourself? You should ask yourself, okay, is it 1 or 2 populations or 1 or 2 samples? Is it proportion problem or a mean problem? And then you should be able to pick your test. So then let's say, so if you were going to actually do this, right, you would have to be able, for your new drug and current drug, get the mean and standard deviation for your sample. And then you would type in your calculator, the mean and standard deviation for each sample, and you would do your do and get your p-value. And they said that after a method in part A was carried out, researchers found a difference with a p-value of 0.003 in favor of the new medication over the old drug. Does this mean that the researchers can conclude that drug caused a reduction in cholesterol? So what does that p-value tell us?
That we have convincing evidence for HA, which would say yes, that they can say that the new drug was better, right?
Good.
Okay.
Right, because your null is always no difference, that they're equal, or that when you subtract them, it equals 0. So your null is no difference. Your alternative is that there is a difference, and they specified in favor of the new medication over the old. So if you have a small p-value, which this is a small p-value, you have convincing evidence for HA, which in this case would be medication is better than the old medication, that it reduces cholesterol. That makes sense? We good?
Mm-hmm.
Good job. Okay, these last two are talking about all the components of an experiment. So identify, I'll kind of just read through this, and if y'all want to intervene, feel free, but we haven't talked about this in a while, so I might just show the answers and check it that way. But the subjects is who's getting the treatment. So who's getting the treatment is the volunteers. So however you want to word that, but it's the people taking the drug. The treatment is what you're assigning, whatever's randomly assigned. So if you look here, it says they didn't put treatment on this. Oh, they did it in a different order. I guess because that order makes more sense. So let me read it in the order that they put it. So your subjects are your volunteers. Now the factor is whatever you're controlling. So it's just like it's not all the different versions. It's just whatever drug they're taking. Now your levels and your treatments, if you only have one factor, your levels and treatments is the same thing. Okay, that's just the different versions, which we have a current drug and a new drug. And then your response variable is whatever we're recording at the end and comparing. We're comparing the cholesterol level after they take both drugs. Okay, so level and treatment are going to look the same if there's only one thing that you're controlling or you're changing. Now, part H says now they're going to control exercise and they're going to control what drug. So it says they decide to ask volunteers to exercise at a high level, low level, or not at all. And then they also are going to give within each high, low, and not at all exercise, they're also giving a current drug and a new drug. It's kind of like if you made a table and you put high, level, low, current, new drug. Think about there's 6 different combinations. So those 6 different combinations would be your treatment now. So your subjects would be the same, it's still the volunteers, but now you have 2 factors because you have 2 different things you're controlling. One is the type of drug and one is the amount of exercise. So your level is separate. It's the different versions of each factor. So you have 2 levels for the drug and 3 levels for the exercise. So then now your treatment is each combination. So now once you have 2 different factors, level and treatment aren't the same anymore. Level is just how many different versions you have for each factor, and then treatment is all the combinations combined. So you would have 6 treatments: current high, current low, current none, new high, new low, new none, if that makes sense. I would think about it as a table, putting each factor on each side of the table. Does that make sense? So just think about treatment as the end, all the different combinations. So if you only have 1 factor, combinations is just the different type of versions they give. But if you have 2 different factors, it's going to be a little bit more. Okay. Any questions on those before we move on? I know I'm only left with, I think, 3 of y'all now. Yeah. Did Molly leave? Yes. So I appreciate y'all for sticking through. Y'all get something. If it's not just love in my heart, it'll be something better. So we'll go through this fast since, again, I don't have many of y'all, but I want to go through the other stuff I posted in the last kind of couple things you could do to prepare for your AP test. Choosing inference practice. I don't know if I feel like it's been a while since we practiced chapters 8 through 10 in a good amount. So what I did is, if you go to your Google Classroom, the last thing, well, I'll start from the top. This is just our Google Meet information. Here is a bunch of stuff. So this inference review is, they give you a bunch of questions and you get to just pick what type of test you would do. Is it 1 sample Z interval, 1 sample T, 2 sample Z, 2 sample T? Now the thing is there is some like T interval for slope. If it's talking about a slope, that was chapter 12. You don't need to worry about that. If it's chi-square, we did learn that, but it's not going to be on your test, so you don't need to really worry about that. So really you just need to worry about this top. They have interval and then they have test. So are you going to do a confidence interval or are you going to do a significance test? And so you just read the question and you just decide which test. Okay, that's really good practice if you need practice on picking what inference you would do. And then the answers are on this next page. I'm not going to show them because I don't want you to look until after you try it on your own. So use this wisely. Don't just go look at the answers, but actually answer it on your own. And then you can go check yourself on the second page. Okay, so if you have any questions as you're working through that, just let me know. And then I also put on here, this is a more in-depth. That one you don't have to actually calculate anything. You just pick what the best test or what name you would, what method you would write down. This one, it actually wants you to work it out. So you pick your type of test. So I think this is all hypothesis tests. There's no confidence interval. You pick your type and then you actually set up your hypotheses and then you write down your requirements. Those are your conditions. And then you find your test statistic, your p-value, and then what does that mean? Would you reject or fail to reject, HO? So you actually are doing kind of like a significance test. And there's just multiple examples. Okay, so this is just kind of for you to use as you feel like it would help. So this is not required, but if you feel like you need more practice on inference, I would suggest doing that. And I will post the answers, or if you just reach out to me after you do it, I'll send you the answers. Either one, just let me know. So that's if you feel like you need help with inference. I also posted these links. So I feel like something we haven't practiced in a while is combining random variables. That's chapter 6, and transforming, where remember you can't add, if you're combining the time it takes you to get to work and the time it takes you to get home from work, you can add the means, but you can't add the standard deviations. You have to add the variances and then square root. And then even if you're subtracting the difference from the time it takes you to get to work, from the time it takes you to get home from work, you still add the variances. You never subtract. So those type of concepts, I feel like if you need some review on that, here's some Khan Academy, just quick practices on that. And then if you feel like you need more work on probability, here's a Khan Academy test on probability. So from here on out, it's kind of what you feel like you need more work on. Do you need work on inference? Do you need work on probability, random variables? You be responsible and decide what would be most beneficial for you. Okay, and then if you need any other materials to review different concepts, just let me know. But I don't want to overwhelm y'all with too much, but I want you to have what you need to review. So that is that. And then the last thing is I put these interpretations. So that's this one, I didn't make this. Okay, so if you look, here's just a bunch of definitions. Here's stuff about sampling and experimental design, like chapter 4. And then this is like state plan do conclude, but they call it panic. I don't think it's a bad idea to look through this. And even though it might word things differently, you should be like, oh, okay, that's the same as this. You should be able to recognize the similarities and that it's the same thing in the end. So it talks about confidence interval, state plan do conclude, what a confidence level is, margin of error, sample size, how to find a sample size. We haven't done that in a while, so that would be worth looking at. And then it talks about hypothesis testing. So it's just a review page that is worth looking over. And then this sentence summary is another review page of just certain interpretations that we use a lot. So these two things is what I meant when I put on the schedule for like next Tuesday. There's nothing for you to really work through, but you need to read through it and just kind of combine the best of everything. Okay, whatever makes most sense to you, you need to get all that stuff together and make sure you're familiar. Okay, where in your review stuff is confidence intervals? Where in your review stuff is probabilities? You need to kind of start to organize and think through, what are you going to use on your test? What are you going to have in front of you? Okay, so these are two just tools you can use to create your review sheet that you want to use for your test. So that's the top two, and then the bottom two is practice for hypothesis tests and confidence intervals. Here's your formula chart. You should definitely have this printed and in front of you for your test. And then the tables if you need the tables. So the first two tables are for z-scores. The second table is for t, when you have a degrees of freedom. And then this is chi-square, which you won't have on your test, so you don't really need that one. So your goal from here on out is to just practice what you feel like you need the most practice on. And if you need more tools to review stuff, just let me know what you need. And then also consolidate and figure out exactly what you're going to have in front of you for your test. Okay, lastly, what you need to do logistics. So that's what you need to do, like content AP stats wise. What you need to make sure you're doing to be ready for your actual online test is, I think on Wednesday, that's 2 days before your test, you need to start looking for your e-ticket. You need to make sure you do your demo test and you decide what device you're going to take it on. Are you going to use your computer? Are you going to use an iPad? Are you going to type it, or are you going to handwrite it and take pictures? You need to figure that stuff out. If you need the link to the demo test, let me know. I'm not sure if I ever posted that on y'all's Google Classroom or not, but I'll repost it when I'm done here. And then if you're going to handwrite, you can do this later when we meet next time, but you need to prepare your pages ahead of time by putting your AP ID number, your initials, and then page number 1 through 5 for question 1, and then do the same thing for question 2. So it should be 10 sheets of paper, but 1 through 5, and then 1 through 5. And then you also need to print your formula chart and any other resources you will use. So I know that was a lot. I just feel like I was just like, but that is, I will post this recording if you need to listen to anything, and also post the PowerPoint. But I think that is all. So you got a week to just kind of get yourself ready, do any last minute things, but I'm not going to have anything assigned other than, well, not other than, I'm not officially assigning any more work. It's just kind of what you need to do. Okay. Any questions? We good? Y'all are almost there. And then you're going to be done with high school forever. So enjoy the last week. I know it's so fun. Well, that's all I have for y'all. So unless y'all have questions or just want to chat about anything, y'all are free to go. Thanks for joining again. I'm gonna remember that y'all were my 3 that stayed. It'll mean something in the end. And if y'all are watching this recording, it's nothing against y'all. They're just better. I'm just kidding. Okay. Well, I'm gonna stop recording, but y'all feel